Okay, so I'm going to start with the basic notions of extreme value laws and what does it mean to prove the existence of an extreme value law. Okay, so for this moment I'm in the classical setting, so we just consider a stationary stochastic process where the marginal distribution function is denoted by f. The tail of this distribution function is given by this f bar, and the UF will be the right endpoint, the right endpoint of the support of this distribution function. Okay, so we say, this is to introduce some vocabulary. We have an exceedance of the extreme of the level u at time j if xj exceeds u. Then we define the maximum mn of the first n random variables, and the idea is try to show a distributional limit for mn. So the difference here is that in the usual study in statistics, one usually studies averages, and instead of taking averages, we just take the maximum of the first n random variables. But then what we want to show is if we can prove some sort of distributional limit for mn when properly normalized, as pretty much one does when studies central limit theorems, for example. So we say we have an extreme value law if there exists a distribution function h which is not degenerate, and by degenerate I mean something that goes from 0 to 1 in one step. So this would be being degenerate. This would be continuous on the right. So this would be a degenerate thing, and non-degenerate means exactly not this. And so we have some distribution function h that it's non-degenerate, and we say it's going to be an extreme value law for mn if for sequences un satisfying this condition, then the probability of mn being less than that thresholds un converge to this h bar of tau, where tau appears here in the normalization factor. Now, to understand the idea for this normalizing sequence, we go to the IID case, where we can easily understand why un, if un satisfies that condition, then it's easy to show that you get a limit for mn. So if you are in the IID case, then saying that the maximum is less than this threshold un is saying that all the random variables from x0 up to xn minus 1 are less than un. And of course, if they are independent, then one gets the distribution function of one of them raised to the power n. Okay? Then you can easily just, instead of writing f of un, is write 1 minus the probability of exceeding un, and this is raised to the power n. And then you realize that if you put something here, if this thing here behaves like tau over n, then you get this standard limit that this goes to e to the power minus tau. And of course, if we see the condition we've put on un is exactly that this thing behaves basically like tau over n. Okay, so for independent and identically distributed random variables, basically what one expects is this sort of limit, where then, of course, if we do some linear scaling, then this tau may have some different shape, but in all cases, we have an exponential of something. Now, this would be in the independent setting, but in the beginning of the 80s, gave a condition that he called dun And so now I'm going to remove the assumption that the random variables are independent, but I'll have some sort of asymptotic independence or some mixing condition. So the mixing condition dun here basically says that if you consider two blocks of random variables, well, one depending on the two events that depend on the two blocks of random variables. The first block depends exactly on the random variables indexed by i's, so from I1 to IP, and the second block from J1 to Jk, and there is a time gap between the J block from the I block, and this time gap is of size m. Then if you look at the dependence between the events not exceeding un in all these blocks, the I block and the J block, compared with the product of never exceeding un on the I block times the probability of never exceeding un on the J block, then you get some rate here. And this rate, which depends, of course, on n, because n has got to do with the size of the threshold you put there, and m, which is the size of the gap between the blocks, then one requires that this thing here goes to 0 when nn, which is replacing now the time gap, goes to infinity, but slower than n. So you have some sort of mixing, saying that if you have two blocks, they become more and more independent, and you have some specific, well, at least some rate at which you want this to go to 0, depending on this sequence n. So you must find something that goes to infinity less than n and still creates asymptotic independence between these two blocks. So if you have this condition holding, then it's a famous Lev-Bethe result that the only expected laws are exponential, with possibly a parameter there that is called theta. Now this theta is what has been called in the classical extreme value theory the extremal index. Okay? And to explain basically what it means, let me try to make here a picture. Fancy. Now, so the idea is one is looking at observations. And you have some observations, and you have some thresholds, un. And basically, you are worried when you go above the threshold. Okay? So at some point, you exceed un. Okay? Then you go on, then at some point, you exceed un again. Okay? So in this case I've just drawn, then the theta there is going to be equal to 1, because the theta is going to measure what's called the intensity of clustering. So in here, basically, the exceedances appear scattered along the timeline. Now, it may happen that there is some sort of short dependence that obliges the exceedances to behave in clusters, to appear in clusters. So it means that, well, probably you look at more things here, but then when you have an exceedance, it usually appears in a block of exceedances. And so on. Drawn with the same number, let me change the number because they don't have to be the same. Okay, so now when you look at data that looks like this, then you have what's called clustering of exceedances, because when an exceedance occurs, then there are other exceedants just nearby in the time frame. And the size of these exceedances is measured by the extremal index in the sense that the average size of the cluster, so this would be a cluster of size 4, this would be a cluster of size 5, the average size of the cluster is 1 over theta. So intensive clustering means that theta is close to 0, and no clustering means that theta is 1. Okay? So basically that's the interpretation of the extremal index. Wow. Intelligent thing. Okay, so so this would be the extremal index. And now, Joe, now this is just a comment about people who work on probability theory usually know this theorem, the classical types theorem for extreme values, which essentially asserts that there are only 3 types of distributions that one can observe when the sequences, the normalizing sequences, are linear sequences. So if you have linear, so you study linear sequences, which means that UN is basically of this shape there, depending on some y, then what you can say is that when you put that condition that n times the probability of x0 being larger than un goes to some tau, then this tau is going to depend on y. And one can actually show that there are only 3 types of taus of y, let's say, that can appear. So this corresponds to the first type, which is also common known as the Gumbel distribution. So this would be e to the power minus y. Then this would be e to the power minus y to the power minus alpha. And then this would be e to the power minus y to the power alpha. Okay, so there are only these 3 types of taus that can appear if you consider linear sequences. Okay. So, but in this setting, I'm only worried about the existence of a law. So, of course, depending on the observables I'm going to choose next, the taus are going to be different. But I'm only interested here in the fact of there exists a law or not. So they won't play much of a role here. Now, the idea is now to put this probabilistic probabilistic theory in dynamical system context. And so for that, we take a system where X is a Riemannian manifold, B is just a Borel sigma algebra, F is your discrete dynamical system, telling you how transitions from certain state happen. And P is just an F invariant probability measure. And then what one, if one wants to study probabilistic properties of this system, what one does is consider stochastic processes arising from this system simply by choosing an observable function that we call phi, and then evaluate this observable function over the orbit of the system. Okay? So in this case, we are going to assume that phi is going to achieve a global maximum at a certain point zeta, but zeta can be any point in the phase space. And we allow phi to actually take the value plus infinity at that point zeta. And basically, we assume that some regularity on both on phi and p, so that these 2 conditions R1 and R2 hold. Okay, so let me try to give you an idea of what. There's no eraser. Here. So basically, I'm going to take phi's that behave like some g of the distance. So these ones would work, but we can actually, in the theory, use more general phi's. But in order to have an idea of what I'm thinking of, these ones will suffice. So take g, take the distance from some point x to some point zeta, which is fixed on the phase space. Okay? Now, g can be something that I'm only interested in the behavior of g near 0, so g is just defined from in a small interval near 0 and is decreasing in this interval. So say like G something like this, or may have an asymptote, something like that. Basically, this will tell you that if, let's say, you have a one-dimensional manifold, so let's say you have an interval, just to make things simpler. Let's say you have 0, 1. And then you have some zeta, which is fixed on the phase space. Then I'm thinking about some observable that achieves a maximum at some zeta. Okay? And then the first condition, R1, that I'll put there in a minute, tells you that if you exceed a certain threshold, let's say U, and U is close to UF, what's UF? UF is exactly the maximum. It's just phi of zeta. So if U is sufficiently large, then exceeding U means that you enter some vicinity of zeta. So basically, that's the picture I want people to have in mind when I talk about this condition R1. And so I want some, so here I'm thinking about that the measure is nice, so I'm thinking something like behaves like Lebesgue, for example, and the observable function is a continuous function, for example, like this, and in this case, of course, R1 is going to hold, okay? But I repeat, I only need this R1 and R2 to hold, and for that I can have singular measures with respect to Lebesgue, and I can also have more general observables. But in any case, that's the picture I want to have in mind.
But you still keep only one point Z.
Yes, but we still
fine with this like a glass with many local minima. Then you should somehow include the
other R points. Yeah, well, here in the theory, you basically do for one zeta. But if you add some finite number of them, it doesn't change. It doesn't change much the theory. Okay, if you add a sequence of them, then things can get nasty. Well, for example, you can change the extremal index, for example. Okay, but here, there's only one. So this would be the picture for R1. So for R2, I'm worried in the case that zeta is a periodic point, okay? And I want also some regular conditions to hold. But, well, these are pretty much natural if you consider that zeta is a repelling periodic point. So basically, now let me do a two-dimensional picture here. So instead of looking at balls-like intervals, let's think now that we are in a two-dimensional thing. And so I have zeta here. And I'm just drawing this ball there, okay? So if zeta is periodic, and if it's a repelling periodic point, then one knows that there is some set, some ball smaller than this one, that after some p time, which is actually the period of zeta, comes back and it's the original ball, okay? And I want that the measure and these sets scale in such a way that the probability of being in this smaller ball, which is what's written here, basically scales this way, okay? And of course, if you have a map which is differentiable, for example, and if your measure is like Lebesgue, then the theta here would just be 1 minus 1 over the determinant of the derivative at zeta. Okay, so it's just the natural scaling if it's Lebesgue measure. So it has got to do with the expansion you have at the periodic point, which tells you how you go from a neighborhood like this to this one. Okay? Now, what we want to do is to count the number of exceedances. Because if you're doing some extreme value analysis, then you want to know how many exceedances occurred in a certain interval of time. And so for the moment, I introduced this quantity here that I'm going to rescale in a minute in order to get some limit. Otherwise, this won't converge anywhere. But the idea is you have a stochastic process, and I have some n view that counts the number of exceedances when j is just an interval. Okay, so you think of any interval. Now you intersect with the integers, and you see for the integers that fall into this interval if you have an exceedance or not. If you have, then you count one more. If you don't, you just do nothing. Okay. And then we observe that, well, there is another relation with what's called the first eating time and first return time that has already appeared in some in ergodic theory in the 90s. And so for that, I introduced this notion here, which is the first eating time to a set A. So now fix a set A in the phase space and define the first integer such that it's the first time your orbit goes inside A. Okay? So this would be the first eating time. And then one can easily understand that there is a relation between eating times and the maximum, when the maximum is for observables of this type. Because if the maximum never exceeds you, then that's because you've never entered this vicinity from 0 up to n minus 1. So basically you are saying that the first eating time to this set U of U is just the corresponds to x0 larger than u, then the first eating time to this must be larger than n. Okay? So if I'm saying that my observations are always below this threshold, then that's because I'm always outside of this set there, and so the first eating time to this set must be larger than n. Okay? Now, as I said, in the 90s, started appearing, well, actually earlier with the work of Pitsko, for example, but I'm talking about the papers of Hirata and Sandro, Benoit, and Hirata again, well, and then lots of papers about eating time statistics and return time statistics. And the idea was to study these eating times when the target sets shrink. Okay? And so we say that we have eating time statistics if you can get a distributional limit for this eating time when these balls shrink, and you use some normalizing factor there, which comes from Kak's theorem. Okay? And in this case, we have eating times, and if you start in the actual target and you consider the measure conditional to being in this target, then instead of having eating times, you have what's called return time statistics. And then there is a beautiful result by Lacroix, Sandro, and Nicolai, right? Where they give an integral formula that relates this G with this G tilde. So it means that if one limit exists, the other must exist, and there is a formula that relates the two. Now, as one can actually forecast from this relation here, there is actually a connection between proving an extreme value law or proving eating time statistics. And so this was motivated by the work of Collet in 2001. And basically, myself, the other F is my wife, and Mike Todd, which is now a long-time collaborator of ours, we proved that if one adds eating time statistics with a certain G distribution function for the limit, then actually, when you look to observables of that type, then you also get an extreme value law with the same distribution. And this goes the other way around. If you prove an extreme value law, then you have eating time statistics with the same distribution again. And I remind you that in here, we are talking about target sets that are poles centered at zeta because of the way we show the observables. Okay, so this is the first result. Now, what one wants to do is to study. So basically, what I'm saying is, if one looks at this, we have two perspectives to look at the study of rare events in dynamical systems. Either one looks at eating times or return time statistics, or one can look at extreme values. And basically, they're two sides of the same coin. Okay? So now what we want to do is carry the analysis a bit further, and instead of looking at the behavior of the maximum, we look at the behavior of what we call rare events point processes. So instead of looking at events of the type n less than or equal than un, which means that up to time n there are no exceedances of this threshold un, we want to study something more general, which is the number of exceedances in a certain interval when properly normalized, and try to find a distribution for this rare events point process. Okay, so basically what we are going to do now is we are going to count exceedances, and for trying to look at a distributional limit for that, we have to normalize or to make rescale time in order to have some limit. So the idea is we rescale by this factor Vn, and this Vn is given by Cox's theorem again. And the reason why we need that is, so when you want to look at convergence of processes, you want to look at things in a certain interval of time. Of course, since your observations are integer valued, and your thresholds are growing, then the expected number of exceedances in an interval like this is going to 0. So what you do is you change you make a time rescale so that the number of exceedances is basically kept constant. And the time rescale is done by that factor, which is exactly the expected waiting time between two exceedances. Okay, so we look now at this way of counting exceedances in a certain interval j, rescaled in time by this factor Vn. And so basically, in this rescaled time, we count the number of exceedances that appear in that period of time. And we call this the rare events point process. And one can realize that, for example, if you consider your interval j to be 0, 1, for example, then by the factor that we're using there, asking for the probability of an n being less than un is simply equal to the probability of an n in 0, 1 to be equal to 0. So asking for the maximum not to exceed un is just equal to the probability of having no exceedances in this interval when properly normalized by that sequence UN. Okay? So of course, if you know the behavior of this, then you'll know that. So this is more general because, of course, I can put other values other than 0 there. Okay, now these processes that I've been talking about are going to converge somewhere. And that somewhere is a compound Poisson process. And in some cases, actually, we actually get the exact Poisson process, the standard Poisson process. In some other cases, we get some compound Poisson distribution. So in order to make things clear, I'm going to I have this slide here to say what we mean by a compound Poisson process. So for a compound Poisson process, we consider so basically we have the timeline, and then we have the compound Poisson as, let's say, two components. One has got to do with the Poisson events that are ruled, that give you the that are ruled by an exponential distribution. So you look at, you are interested in some certain occurrences, and these occurrences appear in at some moments, and the waiting time is ruled by an exponential distribution. So it means that when you want to count the probability of having a certain number of occurrences in a certain interval, you get a Poisson law. Okay? So you have some T1 will give you the waiting time until the first occurrence. Then you have to wait some time T2 for the second occurrence, and then you have the second occurrence here. Maybe you have the third occurrence there, and so on. Okay? And these T's, as I said, are independent identically distributed exponential random variables. And then you've got some other random variables that we call D1, D2, and so on, which are independent between themselves and also independent from these T's, and that give you the multiplicity of each occurrence. Okay? So for the standard Poisson process, the multiplicity is always 1. So in here, you might have some different multiplicity, but in the cases we are going to consider, the multiplicity is always going to be integer valid. Okay? So you might have something that is size 2, here might have something of size 1, here might have something of size 4, and so on. And so the compound Poisson process has to do with these two components, and then you want to study what's the distribution of the number of occurrences counting multiplicities is equal to some value k. Okay? So for example, here, let's say you have some j. N of j would be, well, there are 3 occurrences. The first one occurred with multiplicity 2, the second one with a multiplicity 1, and the third one with a multiplicity 1, 2, 3, 4. Okay? And so that's how you create a compound Poisson process. And when you have, and there are 2 particular cases of these compound Poisson processes that I'm interested in. One is when the probability of the multiplicity being 1 is 1. So in that case, you have the standard Poisson process of intensity 1. And the other case is when this, the probability of having multiplicity k, where k is an integer, is given by this geometric distribution function. So in that case, if you want to know the probability, of having k so that n counts equals k, where this counts the occurrences with weighted by these multiplicities, then you get what's called the Pauli distribution. Okay, so these are the two limits that I'm going to talk about, that are going to appear in a moment. And now here is the basic assumption for our results. So for our results, we use the assumption that the systems have decay correlations against L1. Okay, so first, what is decay correlation? So we consider two Banach spaces, C1 and C2, and we now consider these observable functions phi in C1 and psi in C2, and we measure the correlation between phi and psi after n steps, simply by computing the covariance with respect to the invariant measure p, and dividing here by the norm of phi and the norm of psi, so that you get a correlation factor. And we say that we have decay correlations with respect to this p of observable C1 against observables in C2 if for every phi in C1 and for every psi in C2, this quantity here goes to 0 as the time gap n grows. Okay? Now we are particularly interested in the case where the second Banach space is L1. So actually L1 with respect to P. And so in that case, observe that the norm there is the L1 norm of psi. Okay? So our basic assumption is that we are going to ask the system to have decay of correlations against L1, but the decay of correlations is summable. Okay, I've put there n minus 2 so that you get the idea, but in fact we only need that this thing is summable. If this thing sums and it's finite, then it's okay. So if we have this sort of decay of correlations, then this result, which is divided in two parts, so the second part here was obtained with me, again, my wife and Mike, and the first part was obtained with myself, Ale, Itak, and Sandro. This result actually tells you that you have a dichotomy in terms of the limit clause you expect for the rare events point processes that I have defined before. So basically, if your system has decay correlations against L1, then for the stochastic processes that are constructed in the way that I've been mentioning here, which achieve a global maximum at some zeta in the phase space. And then what we realized is that there are only two types of limits. Okay? Either the rare events point process converge to a standard Poisson with intensity 1, which means no clustering, or the zeta is a periodic point, and in that case, the rare events point processes converge to a compound Poisson process with a geometric distribution for the multiplicity, which depends on this theta, and this theta has got to do with expansion rate at zeta, pretty much as I wrote here. Okay? Now, the point is that this is a full dichotomy. There's nothing else. Okay? So, for example, from previous results, one would expect that this would happen. Well, even from Mirata's paper, it shows that at periodic points there's some sort of, it didn't look into rare events point process that was done by Sandro and Valiente much later, but in any case, it pretty much expect this theta to appear. And there were lots of results with more general systems even than what we consider here, proving that this variance point process should converge to the Poisson. But this was for almost every point in the phase space. Okay, so here we completely close the gap. So either it's a periodic point and you have that, or if it's not periodic, then you're always going to see non-clustering of extreme values, and it always converge. Okay. Now, so this statement as it is now appeared there, but there are some related results. Well, I'll get to them later. There's now also a result by Keller proving the same thing, but with a different assumption. So he has a spectral gap for, assuming a spectral gap for the proof of Williams operator of the dynamical system. And basically, almost in the same setting as well, there's some results by Mark Policott and Ferguson, where they study escape rates, which allow them to get also a dichotomic behavior in terms of extreme events, except that they don't consider variance point process because they are studying escape rates, and at the moment the mass escapes from the hole, and that's it. Well, in here we are studying this multiple occurrence of rare events. But in any case, so there are some related results now, and there's also a very recent paper by Kiefer and Rappaport, where they also obtained the same dichotomy, but in a different setting and also for non-conventional sums. Okay, so let me try to give you some systems for which you can observe, so to which you can apply this theorem. And the main thing is you have to find systems which satisfy these decay correlations against L1. So here's a list of them. So uniformly expanding maps on the circle. So let's doubling map, for example. Markov maps. Piecewise expanding maps of the interval, like Richlik maps. So I'm just going to give an example there for Richlik maps. And higher dimensional piecewise expanding maps, like the ones considered by Benoit in his paper in 2000. Okay, another remark. Okay? Now, the theorem applies to these systems with decay correlation against L1, but decay correlation against L1 is in itself a very strong property. Because although I only require the decay correlations to have a polynomial rate, which was summable, in fact, from a recent result of ours, the simple fact that decay correlations against L1 exists implies that you have exponential decay correlations, but in some different function spaces. All the observables against L infinity. The reason is that if you have decay correlations against L1, then you can build a Young tower, and you can show that in this Young tower, the tail set of the return times basically is determined by the large deviations which depend on these decay correlations against L1. And so basically one can actually show that decay correlations against L1 summable implies exponential decay correlations in a different function spaces. Okay, so this says that decay correlations against L1 is a very strong property. In fact, in all these examples you have there, the way I know that there is a decay correlation against L1 is because someone proved a spectral gap for the proof of Venus operator in the right function spaces. Okay, so the one question is, what is stronger, this or the spectral gap? And we don't know, but for example, we know an example of decay correlation against L1 that doesn't come necessarily from a spectral gap of the original system, although it has got to do with the spectral gap of some inducing map on the system. But in any case, it's a very strong property. I have this remark, which is just got to do with the part of, I don't think I have time to get there, but in any case, just to tell you that what happens when you add noise, okay? So if when if you consider some point x and then you go to f of x, follow its orbit, and now if you add noise, which means that you may end up somewhere here because you make some mistake, and then you follow again the map f, and then you add some noise again. And if your noise is additive noise, then what we proved in here was that this part simply vanishes, and you always get that for all points. Okay, so it's like a smoothing effect. Adding noise clears out all periodic type of behavior. And so what we've proved in this paper here was that the rare events point process, when you consider additive noise, as long as you have, again, systems with decay correlations against L1, then the rare events point process converge always to the standard Poisson process. Okay? So let me give you an example. So consider a Richelieu map. So a Richelieu map can be something like this. Okay? This is a very special kind of Richelieu map, but it just makes things simpler. A Richelieu map may not be full branched. This one is full branched, but take a map like this. Okay? Now you put some thermodynamical formalism there, consider some Gibbs states and some equilibrium states, and you can apply our theorem to these maps, which basically says that if you have a Richelieu map and if you have some invariant measure which is an equilibrium state, as long as its density with respect to the conformal measure is larger than some constant larger than 0, then when you look at the behavior of the rare events point process and you construct these things the usual way, then you have again this dichotomy, saying that if you have a periodic point, then you're going to watch as a limit for the rare events point process, a compound Poisson process, again with a geometric distribution function. And the extremal index is given by this quantity here that, of course, has got to do with this when the potential is minus log of the derivative. Okay? And also, well, if the point is not periodic, then you're going to converge to a Poisson process of intensity 1. Okay, so this is just an example. Now, some other thing we studied in this AFV13 paper was the case where, so if you look at our assumptions, we assumed a continuous dynamical system. Okay? So for continuous, you have this dichotomy. Now, the problem that we also studied was, what about the case in which you have some points that are where the map, the dynamical system, is discontinuous? What could happen to the convergence of this rare events point process? Well, we've got some nasty result here, but I'm going to just show you how it looks like. Okay, so you've got all these possible behaviors. So I just chose the simplest one to illustrate what could possibly happen. Okay, so now the idea is the following. So we are going to assume we have, well, maybe I should, okay, before I go to this, let me just make a comment on how you understand this geometric distribution, okay? So why should the geometric distribution appear when you have a periodic point? Okay, so if you have a zeta, and you know that we are studying entrances into this ball, then there is, if zeta is a periodic point, it will create a cluster because there is some ball here inside that is sent again to the ball itself. And so after p time, you immediately have, if you have an exceedance and if you fall into this ball, you immediately have another one, okay? And it may be even worse because you may go even closer to zeta and you can find some ball that is sent into this one, which will be sent into this one. So it means that if at some moment your orbit goes inside this ball, then you'll have a cluster of size 2 because you'll go here and then there and then you exit. But if you can even go closer to zeta and so on. And so you have some sort of layers here that tell you how damaging was your first entrance. And so basically, if you have this threshold UN, and if you go very deep, means you have a very high exceedance, then you do this until you at some point exit, and this will mean you create some clustering of this size. So in order to study the cluster distribution, what you have to estimate is, so what's the probability of having something of say size 1, 2, 3, 4? Then that's because in these layers you went into the, so 1, 2, 3, you went into this ball there, and then so you are in a certain annulus, and you do this until you exit. And now, how do you find the probability of that? Well, estimate the measure of these things. And if they scale as I said they would, then the size of this ball here is basically 1 minus theta times the probability of x0 being larger than un. Okay, but then we're going to divide by this, so basically it's this 1 minus theta I'm worried with. Then if you go into this one, then instead of 1 minus theta, then you have a square there. And if you go farther, then you've got some k there. And of course, before you exit, you enter this annulus. And this annulus has exactly size theta. So that's how you see the geometric distribution, okay? So now, let me give you an example. So this was to explain better in 2 dimensions, but now let's try to see it in 1 dimension. And let's suppose you have some zeta here, but now zeta, on the contrary to that one, is a discontinuous point of the map. And let's say if it's a discontinuous point, basically what it tells you is that you're going to study 2 different stories. One is when you look at the iterates as if you went on the left side, and the other one is the iterates when you go from the right. Okay? And now you study the iterates of this guy and this guy. And the picture I had there was for the following case. Was the case in which from this side, from zeta minus, you never get back to zeta. You'll be wandering over the space, but you don't get back to zeta. And for zeta plus, you do get back. Okay, there is some moment at which you came back to zeta. But the following happens. So I'm assuming expansion at zeta, so that this interval here, after say some p plus time, it comes back and covers this whole interval here. So it kind of changes from the right side to the left side, so that now when you look at the iterates, you don't come back anymore. Okay? So when this happens, then it means that you may have clusters. And of course, the clusters, what possible size do they have? Well, they have size 1 if you fall into this part. if you fall into this guy, because this guy, after p time, is going to be sent there, so you are outside the ball. But if you fall into this one, so you'll have cluster of size 1 plus another hit here, and then you never come back, and so a cluster of size 2. And since you never come back from this side, then that's it. You don't have any more entrances that go into account for the rare events point process. And so what you see is that the rare events point process converges to a compound plus 1 process, but in this case, P1 takes this value, P2 is also positive, and Pk is always 0 for k larger than or equal to 3. Okay? Okay, so basically, that's it. Let me just tell you that now. So the dichotomy has been written in terms of decay correlation against L1, and in an ongoing work with Anna Cristina, Sandro, Sandro, and my co-author is complaining, and Mike. Well, using some way of passing the for using results from the first return time map, we can pass the results from this one to the original system, and so we basically get that the dichotomy is going to hold for maps with an indifferent fixed point there, like the Liverani-Sossol-Vaienti map or the Manville-Pomor, with a special case that has got to be treated, which is that one there, because the extremal index there is 0. And so you have to find some other normalizing sequences so that you can actually get a law, but we can do that. Okay. So I'll stop here.
Thank you very much.
Some references.
Questions or comments? Okay, go ahead.
Yes, I have a question. I was trying to rethink again of this problem of this compound Poisson process and what it means, the fact that you have a composition when you have a periodic point. Okay. So I was thinking, and then you say, okay, I have a waiting time, which is, let's say, exponential, and then I can have 1 or 2 shots. What if you say, because it seems to fit also with the idea of the effect of noise, that instead your waiting time is, you have a different role for the waiting time. The waiting time is an exponential plus a constant times delta of 0.
Mm-hmm.
So you can have 0 waiting time. So these are not 2 events. It's not 1 event counting 2. It's 2 events separated by 0. And then my impression, maybe when you add the noise and you do this sort of, you do some sort of averaging basically, because you do the product of probability, if you have the delta, as soon as you have noise, it's dead. It's going to distribute everywhere.
Right.
So you regularize it.
Mm-hmm.
So my impression is that you could treat the existence of a periodic point as the fact that in a neighborhood of your point, you have you just have a repetition. So somehow it's a different rule.
Mm-hmm.
But you might treat it together by putting an expectation time which is 0 with a finite probability. With the probability is related to the neighborhood you're considering of your points. I don't know, it's just something I've been thinking about now when you were talking. I don't know if it makes any sense, because then you will treat these clusters, or not time 0, just time 1 or p, I mean, whatever you want to consider.
Mm-hmm. But you mean by after the normalization is done? Because what's happening here, for example, is that so you see,
okay.
The thing is, you have this cluster, right? Well, if the point is not periodic, actually, you may see something like, so you exceed, then you wait some time, and then you exceed again because this is p time, right? But what happens is that the normalization kind of smashes everything and puts everything in the same
because that
occurrence.
counts as 1. It's
Yes.
just an illusion of a class.
Yes.
So that's exactly what I mean. I think you can distinguish in this way just the fact that the expectation time, by chance, you get a short interval from an interval which is genuinely short.
Okay.
So, and that would survive the normalization.
Hmm.
It's just an idea. I don't know even how to say it precisely, but I have the impression that you can treat it, and it would describe exactly the sort of recurrence.
Periodic and okay. I'll look into that.
I don't know.
Maybe we can discuss it after.
I don't know. Just
Other questions? Okay, well, thank you, John, again.
Yeah. Did you get this?
We got something to do because
How do you get other normalizing sequences? I want, I don't know, a cubic or some bullshit like that. Instead of the linear.
Usually it's done by, well, either they are linear. Okay.
We meet
Yeah,
for an
yes, yeah. So the ones I know, I don't know, at least you know, like, but the normalizing sequences I usually either are linear or are given by quantiles of the distribution function.
of course, yeah. That is the main. Yeah, okay, that makes sense because you are escaping.